So I will be talking on a very game theory topic, like equilibria in large coordination games. And by the way, I have a question. Do you see my mouse? Like if I'm going to be moving it? Perfect. So the starting point is that there are, many social situations in which people's behavior has positive externalities on others. So maybe more specifically, I'm thinking about behaviors where I'm more likely to choose some action or adopt some behavior if people around me are doing the same thing. And we just went from COVID pandemics and we start forgetting about it, but I'm sure that you remember that there were times where you were wearing mask, not so much because of the intrinsic need of wearing mask, but maybe because people around you were wearing mask, or maybe there was a situation on the contrary where you would think wearing mask would be appropriate, but because nobody else around you did, you didn't do it as well. Famous examples of behavior with coordination, positive externalities are political actions where people participate in a demonstration or in a riot because other people do, or are stopped from doing so because they don't think that anybody else will do. Technology adoption and so on, so on. And when people think about this type of situations theoretically, there's large literature on coordination games. The kind of result is always that the equilibrium is emergence of a convention, a homogeneous convention, where convention is really understood as an equilibrium where everybody is doing the same thing. And the kind of question is which kind of behavior will become the convention, which one is more likely to become convention. But in reality, of course, the behavior is typically, so we'll call it fuzzy, but heterogeneous. Like some people do one thing, some people do another thing. Not everyone is wearing mask, even at the height of the pandemic. Another example that's probably less important now, but this was more important, say, 10 years ago, where even married couples using one Android and the other iPhone, without benefiting from the externalities that using the same technology would give them. And the sort of typical explanation of this type of situations is that people do not have the same payoffs, right? Like, so everybody reacts to externalities, but I may feel about externalities in a slightly different way as you. And this was an example that, the sort of explanation that goes all the way to actually political scientist, Granovetter, who wrote this very influential paper with the main example being a demonstration. So, the questions that I want to answer is the following. So first is kind of conceptual. Is there some way of thinking about heterogeneous behavior as a convention? So there will be no one action that everybody chooses, but can we think about this in some sense as a convention? And if so, that's kind of standard question will be which conventions are going to be more likely, which convention we expect to emerge, and then whether this answer depends on some kind of structure of social interactions, which I will interpret in a standard way as economists do, which is the network, how the net of the people interacting with each other. So I want to walk you through some kind of idea behind the model first before I present the main model, and to kind of illustrate some experiments, like simulations more than experiments. So the Granovetter proposed the following model. So the way that he's thinking about heterogeneous payoffs is that everybody has a threshold, and this threshold essentially says the following: I'm going to adopt the action if the fraction of people in the population is above the threshold. And those thresholds have distribution. So everybody has a different thresholds and they have some distribution. And the green line here describes a distribution of the thresholds. So this picture shows a situation where we have three types of people. There is 30% of people who have a threshold below 0. Okay, if you have a threshold below 0, it means that you will always adopt the action, no matter what other people are doing in the society. On the other hand, there are 30% people who have a threshold above 1. If you have a threshold above 1, then it means that even if everybody else in the society adopts the behavior, you are not going to do it. So for you, not adopting the behavior is a dominant action. And there is this group in the middle, the 40% of the population, who have a threshold of value of 0.55. So that means that those people will adopt the behavior only, will wear a mask, only 55% of people in the population will also wear a mask. Okay. So when you, is this graph clear, more or less? So when Granovetter pointed that, well, if this is the distribution of the thresholds, then we are going to have free equilibria. This is an intersection of the distribution with the 45-degree line. And this equilibrium in the middle is unstable. It can be ignored. There will be two stable equilibria. Okay, that corresponds to 30% of people adopting the behavior. These are essentially only the people of the first type. And then somewhere around 70% people adopting the behavior. That means everybody for whom the action 1 is 0 is not strictly dominant will also adopt the behavior. Okay? Now, there is no way of choosing between those two equilibria. They are equally good in the Granovetter model. So what I'm going to do is to take the Granovetter model, who was thinking about kind of society where everybody interacts with everybody, and to put it on the network. And what I mean by that is that my agents are going to live on the nodes, in the nodes of a network, and then they are going to interact only with their neighbors. So the network is going to say who are their neighbors. And when they are going to choose whether to adopt the behavior or not, they are going to look at the average behavior in their neighborhood rather than the whole society. Okay? And the reason I'm going to do it is, one, because I wanted to understand whether the putting them on network changes anything. So the next slide, I'm going to show you that it does. So that's a kind of a little bit complicated slide, so I will explain it in steps. So I ran 4 experiments, so simulations, you can think. They correspond to 2 distribution of thresholds, P1 and P2. P1 is exactly the same as on the previous 2 slides. So we have this 30, 40, 30% groups. The group in the middle has a threshold 55, 0.55. And we have 2 equilibria, A and B. P2 is another distribution of threshold that differs only. The group in the middle has a lower threshold. I think it's like 0.4. So that means that under P2, the people in the middle are going to be more likely to adopt behavior 1 because the threshold where they switch from 0 to 1 is going to be lower. Okay. Both distributions have 2 equilibria in Granovetter model, and you can notice that equilibrium A is bolded here and equilibrium B is bolded here. I will explain in a second why. The 2 bottom lines, they correspond to the results of the simulation on 2 different networks. So let's start with describing what kind of networks are these. Both networks have around 160,000 nodes. Each node, so each individual in the network has around 100, 120 neighbors. In the random graph, those neighbors are chosen randomly. Okay, so it's like Erdos-Renyi network. It's a standard example. In the city network, all the individuals are living essentially in a square. So it's like 400 times 400 people. And their neighbors are all people within the radius of 10 around them. Okay, so this will be overlapping neighborhoods. So the difference essentially between city and random graph, the main difference is that in the city, there is plenty of overlap. So the neighbors of my neighbors are also very likely to be my neighbors. In the random graph, it's very unlikely that is the case. So what are those pictures here? So for each network, I did the following simulation. First, I randomly chosen threshold for each individual, drawing it independently from this distribution. So 160,000 thresholds drawn randomly from this distribution. So now I have 160,000 people each with a random threshold. I'm going to look at equilibria of the Granovetter game. And specifically, because this is really a binary coordination game, I can look at I have well-defined lowest and the largest equilibrium. Okay, there's easy algorithm how to find them. for the smallest equilibrium, I start assuming everybody plays 0. Then I look for the guys for whom playing 1 is strictly dominant. I switch them. Then I look whether anybody else wants to switch, and so on, so on. I keep on going up until I reach the moment that nobody else wants to switch. That will find me the lowest possible equilibrium. I can do the same thing from the top, starting by people who only play the 1 as a strictly dominant action, then going down. And this allows me to find the smallest and the largest equilibrium. And then, so this is for a given realization of threshold. And then for each, the smallest and the largest equilibrium, I compute the average behavior. So what fraction of the society ends up playing action 1? And then I run 100 of those simulations. And then I plot. So for the random graph, the blue graph is the frequency graph of the average behavior in the smallest equilibrium. And the orange is the frequency of the average behavior in the largest equilibrium. Okay, you can see that the smallest equilibrium is concentrated around 0.3 and the largest equilibrium is concentrated around 0.7, which is what we expected from the Granovetter model. Okay, those two frequencies correspond to those two equilibria. Similarly, for the second distribution of the thresholds, I do the same, and you can see that we have some similar picture. Again, we have 30 and 70% of the people playing 1 in 2 equilibria, and they correspond to 2 intersection of the cumulative distribution function with the diagonal. The situation is very different in the city network. Under the first distribution, both in most of the situations, for most of the simulations, both the largest and the smallest equilibrium is around 30%. Okay, that corresponds to this bolded equilibrium A here. For the second distribution, in all simulations that I had, both the smallest and the largest equilibrium correspond to the 70% people choosing 1. Okay. So we achieved some sort of coordination. It means, so the picture here for the city network means that for all those simulations, the distance between the smallest and the largest equilibrium is essentially the same, despite the fact that the Granovetter model predicts 2 different equilibria, 2 different frequencies of equilibrium frequencies, we end up coordinating on one or the other. Okay. So this is one pattern that I will try to explain, and I will have some results to this. The second pattern that I want to explain is that I wanted to understand a little bit better what the convention, how the behavior looks like in equilibrium. And I think it's the left side of the picture here shows one of the equilibrium in this situation here. Okay, more precisely, so you can see that there is a graph of 400 people on one side and 400 people on the other side. Each pixel corresponds to one individual. But instead of plotting an action for the individual, which is going to be varied, it's a heterogeneous behavior, I'm plotting for each individual the average behavior in the neighborhood of this individual. Okay, and I'm using the color blue to denote behaviors that looks like mostly zeros, and color red that looks like a behavior mostly ones. Okay, so what you can see, although around 30% of those guys play 1 and 70% play 0. The behavior is very heterogeneous. When you look at the average behavior they experience in their neighborhoods, it's quite uniform. There are small level fluctuations. Okay, there are a little bit shades of blue, is sometimes a little bit darker, sometimes a little bit less dark. On the other side, I have a picture that looks very different. It's not the picture that I obtained from any of those 2 simulations, the picture that I got from some other distribution of threshold that was much closer to the diagonal. And you can see that situation here is much different. There are big macroscopic differences between the behavior. There are parts of the network where most people see their neighborhood playing action 1, and there are other parts of the network where most people observe neighborhood 0. Okay. So I'm going to refer to this behavior on the left as a fuzzy convention. Okay, so although the behavior itself is heterogeneous, what people see in their neighborhood is quite the same. Okay, this is what I'm going to refer as a convention. And this is going to be my definition. I'm going to say that the behavior is a fuzzy convention X if, in some sense, everybody in the society observes X fraction of their neighbors playing action 1. To explain my result, I also am going to compute X star, which is a maximizer of this expression. Don't worry about this integral for a second. I'm going to explain it in few slides. The point is that this X star, when you compute it, I will also explain is a generalization of risk-dominant action of Harsanyi-Zelten to games with heterogeneous payoffs. Okay, so this is something that I will also explain. Okay, so with those two definitions, I can state the two results that I will have. So the first results is that all sufficiently fine networks, and sufficiently fine will effectively mean each individual has many large degrees, so many neighbors. They are going to have an equilibrium that is fuzzy convention of X star. Okay, so not only there is always a fuzzy convention equilibrium where everybody or almost everybody sees their neighbors behaving roughly in the same way, but also the same way exactly corresponds to the X star, which is solution to this maximization problem. The second result is that some networks, and city network is example of it, this fuzzy convention is the only equilibrium. Okay, so like I showed you this pattern that on city network, all the equilibria tend to have the same average behavior. That's the result that kind of explains it. This second result, both of those results are going to be asymptotic, so they are going to work for, n going to infinity type of networks. But one of the reasons I'm showing you those simulations is to sort of explain that although my mathematics is only about asymptotic results, I don't really think that you need crazily large, n equal to the number of atoms in the galaxy to establish those patterns in sort of the 160,000 corresponds to sort of not a very big city. And I will use those two results to present some equilibrium selection theory. So to kind of explain that this X star is something that I would expect as a most likely convention in heterogeneous game. So any questions at this moment? I will start talking about the model if not. All right, so the model is Granovetter on a network. So the Granovetter thinks about the stems of these thresholds, but there's very natural way of translating everything to standard kind of game theoretic, binary action, random utility coordination games. Okay, those two models are equivalent. So the network is described by Gij. So that's the strength of the connection, and the main assumption I'm making is that this strength are symmetric. So if I'm connected to you, you're also connected to me. If you want to think about Gij being unweighted network, then just think it's going to be either equal to 0 or 1, depending on whether there is a connection. But the paper is stated more generally, like for the all weighted graphs as well. I will refer to the sum of the weights that are going out from individual I as the degree of agent I, that's Gi, and each node will have one agent. So each agent living in each node has IID drawn payoff shock, so that's this threshold. And profile of actions, so actions for each individual is going to be an equilibrium. If for each individual, if the threshold is smaller than the average action observed by this individual in her neighborhood, then the individual I choose is playing action 1. Okay, this beta IA is the average action that this individual observes in her neighborhood. Okay, if the threshold is smaller than the average action played by others, then individual I chooses 1 as a best response, and otherwise 1 chooses 0. Okay, that's the whole model. And two definitions. The first definition is a formal definition of what I mean by fuzzy convention. So profile is a eta fuzzy convention if the average the fraction of the society such that they observe neighborhood behavior that is eta different than X is smaller than eta. Okay, so sorry, I didn't say it very well. So profile is going to be eta convention if, apart from eta fraction of people, everybody sees in their neighborhood people who behave like X or maybe slightly different than X. Okay, the average fraction of people in the neighborhood who are playing 1 is X or very close to X. The second definition is this random utility dominant outcome. So that's this integral that I introduced a few slides back. So X star maximizes expression, and let's think a little bit what this expression is. So when you draw the distribution of thresholds, so it's still the green line, this integral is adding and subtracting areas. So it's adding areas between the distribution and the diagonal that are above the diagonal, and it's subtracting areas that are below the diagonal. And now we want to maximize, choose X star, so to maximize this expression, so to maximize this sum. So you see that for this particular example, X star is the maximum because if we go to the left, then we only can reduce. If we go to the right, we initially will reduce. Later we will start increasing again, but the gain of this area here is smaller than the loss of the area here. So X star is going to be maximum. In the example from the introduction, the first distribution of thresholds, the one that I started my talk with, has the maximum reached exactly at 0.3. Okay, this corresponded to the equilibrium that was chosen on the city network in my simulation. When we go to the second distribution of thresholds, the maximizer shifts to 0.7. Okay, and it corresponds to the equilibrium chosen on the city of network under this distribution of threshold. We can think about a special case of the model as being a deterministic game. So this is a standard coordination game where I play action 0 or 1 when certain fraction of my neighbors is, so I'm going to play 1 if some fraction of my neighbors is playing above 1, and I'm going to play 0 if this fraction of my neighbors is smaller than some threshold. Okay, so here, this is an example of a standard deterministic payoff coordination game where action 0 is risk dominant in the Harsanyi-Selten sense. So what does it mean? If 50% of people play 0 and 50% play 1, then my best response is to play 0. Okay, this is the 50% is somewhere here, is before the distribution, this green line jumps. Okay. Action 0 is risk dominant. As you can see, the maximum of this integral expression is going to be here. We don't want to move to this part because we would have to subtract the large triangle and add only small triangle. Okay. This is to say that this maximizer corresponds to selects Harsanyi-Selten risk dominant action in the deterministic games. Okay, when the risk dominant action is 1, then the maximizer of this expression is going to be also 1 as well. Okay, so these are the two main definitions. Now I will state two assumptions of the first result. So the first assumption is, I told you that the result is going to be asymptotic. So I'm going to say something about all sufficiently fine networks or sufficiently fine graphs. So the sufficiently fine essentially means that individuals have large degrees. The way it is stated is a little bit more general. It applies also for the weighted graphs. So essentially, D of G is the largest possible share of the value of individual connection to the degree of individual I. So Gij is the strength of the connection between I and J, and Gi is the sum of all connections that individual I has. And what I want is that no individual J plays a significant role in the neighborhood of I. Okay, there is no one who is too important in some sense. Okay, that's the first assumption. The second assumption is some limited inequality. So people are not too different in terms of their degrees. Okay, there's not somebody who is connected to everybody in the network and everybody else is just connected to one neighbor. Okay, so this WG is essentially a ratio, the largest possible ratio between strength of the connection of one individual versus the other. Okay, so these are two assumptions. And given these assumptions, that's the first result. The result says that each sufficiently fine network with a large probability has an equilibrium that is also fuzzy, an approximate fuzzy convention X star. Okay, the formal statement says it's a limit. So take any sequence of graphs with the property that the share of the individual connections in the neighborhoods of the individuals converges uniformly to 0. And then the second, that the inequality is bounded across the sequence of the graphs. Then the probability that we have an equilibrium that is also a fuzzy convention converges to 1. Okay, that's the result. So the idea of the proof is, because we are dealing with a binary action coordination games, those games are known to be potential, they have a potential. So here I wrote potential of this game. It's more precisely, it's an ordinal potential, because Granovetter model, I was not really clear about payoffs. It's equivalent to some coordination game with some payoffs, but the payoffs can be different. It's really an ordinal characterization. That's also an ordinal potential function. We know that games with the ordinal potential function, the equilibria of those games can be characterized by maximizers of the potential. Okay, so what I'm going to do in the proof is to show that for almost all realization of the profiles of thresholds, okay, so the profile of thresholds is all those independently drawn thresholds for everybody, the potential function, the maximizer of the potential function is a fuzzy convention X star. I'm talking about a global maximizer. So it is quite possible that this fuzzy convention X star is not the only equilibrium. There might be some local maximizer somewhere else, but there will be an equilibrium that is a fuzzy convention X star. Okay, that's going to be a global maximizer. Now, that's really the content of my result, but given the fact that we are talking about the potential games, there is also quite a theory associated with those games. They are quite important theoretically, and people have found out that the equilibria of those games satisfy a number of robustness properties. So if you want equilibrium selection theories, robustness to incomplete information, there is stochastic stability under some classes of evolutionary dynamics. I just want to mention that. I don't think I will have time to talk about the proof of this result. Maybe if I finish and there are no questions, then I can come back if you want me. So let me just very briefly say that what is the difficulty here? The difficulty here is that this is a random object. This function is a random object. It depends on the random realization of those thresholds. And I want to say something about the global properties of the function. I want to identify a global maximizer of this function. So if I fix a profile A, I have standard law of large numbers type of methods to tell me what is going to be the value, what can be distribution of the values of this function V. I can even compute because that's summation over the many nodes, some sort of version of law of large numbers will apply. The problem is that I cannot just say what is the value of function V for a given one single profile. I need to say simultaneously about all different profiles, because in the end, I want to make a statement that the global maximizer looks like is this particular A, or is close to this particular A. Okay, so that's the difficulty, and to address it, I need to work a little bit harder. I need to be able to have some sort of version of law of large numbers that applies simultaneously to all different action profiles, and that takes me to something which is called in probability like concentration inequalities and stuff like this. But anyway, like if I have time, then I may, if you want, I can talk about it. So let me instead talk about the second result. So far, I have shown that every sufficiently large network will have an equilibrium that is fuzzy convention X star. The second result is to show that some networks, like a city network, all the equilibria on those networks look like a fuzzy convention X star. Okay, so the formal statement of the result is the following. Suppose that my distribution of the threshold has this property that P0 is positive, strictly positive, and P1 is strictly smaller than 1. So this assumption essentially means that there will be some fraction of agents for whom playing 1 is strictly dominant, that's those guys. And there is going to be some fraction of agents for whom playing 0 is strictly dominant, that's those guys. Okay. Then the result says that for each eta, there exists some network such that with probability at least 1 minus eta, each equilibrium is eta fuzzy convention X star. Okay. I will explain the role of this assumption in a second. Okay, but the result is that I will be able to construct a network such that fuzzy convention X star are essentially all the equilibria. So the networks that I'm going to construct is going to look like the city network from the introduction. And it's really example of a two-dimensional lattice. Okay, so the lattice is some sort of, it's what economists called, it's really like a grid. And I need at least 2 dimensions. I can have more than 2 dimensions. 1 dimension is not enough. That's the point that I'm trying to make. The network is going to be characterized by 2 parameters. Capital M is the number of people in the network, and little m is the size of the neighborhood of each individual. And then the network I will construct will have to have sufficiently large neighborhood size and sufficiently large number of disjoint neighborhoods that I can arrange in the network. Okay, so capital M divided by M is essentially the number of disjoint neighborhoods that I can park in my network. The result, the theorem from the previous slide, is about a static equilibrium. Okay, so it's really a statement, give me a realization of thresholds, then most likely, so sorry, for most realizations of thresholds, the all static equilibria look similar. But the idea of the proof is dynamic. So what I mean by that is that I'm going to use a best response process to show that there cannot be other equilibria. So essentially it's going to be by contradiction. Suppose there is some other profile that is far away from the fuzzy convention X star, then I'm going to explain that actually the best response process will have to reduce it to fuzzy convention X star. And the way that I'm going to talk about is that I will start by kind of reviewing this best response dynamics arguments are well known in mostly evolutionary literature, but not only, as contagion. And I will review those contagion arguments from the deterministic case. This was well-studied problems in 90s and the early 20th century, with, I think famous paper by Morris being the last. And then I will try to show how those contagion arguments apply also in the heterogeneous payoff case, where the payoffs are random or randomly perturbed by those thresholds. And then I start by modeling contagion on line, but then I will explain that line actually is not good enough. There is some problem with the line and why I need a 2-dimensional lattice. Okay, that's the plan. So I'm going to start with the deterministic case. I will remind you how the contagion works in the deterministic case. I'm going to assume that 0 is risk dominant. Okay, so what it means, if half of my neighbors are playing 0, then 0 is also strict best response for me. And I want to explain that 0 must be the only equilibrium on well-chosen network. And the network that is going to be well-chosen is going to be line. So how does it work? Well, suppose that I have some group of the initial infectors. So all those contagion arguments, they have really 2 parts. First is that we have to have some reason why some people play 0. Maybe because 0 is strictly dominant, maybe because Morris simply assumes that there is some small fraction of people who play 0 for whatever reason. And this, we think about them as initial infectors, and now the question is whether this initial infection is going to spread to the rest of the society. Okay, so the worst case scenario against spreading contagion is when everybody else is playing one. It's a coordination game, right? Like if everybody else is playing one, this is really the strongest reason why people do not want to switch to zero. We maximize sort of incentive to play one as well. Okay, but if these are the initial infectors, the person somewhere here, they have roughly half of the neighbors on this side of the inside the initial infectors group, and half of the neighbors on this side. Okay, half of their neighbors are playing zero, half of their neighbors are playing one. Because zero is the risk dominant action, half of the neighbors playing zero makes zero being a best response for them. Not only for this individual here, but also for some number of individuals who are slightly to the right of this boundary. Okay. So if we start originally with the blue profile, all those guys, because of the best responses, revising their actions towards the best responses, are going to change into playing zero as well. So now we have a new boundary where all the people to the left are playing zero, all the people to the right are playing zero. But now the argument is exactly the same. We have half neighbors here and half neighbors here because zero is the risk dominant action. This person and maybe some people to the right will switch to playing zero as well. And so on, so on. Okay, the contagion is going to spread. The risk dominant action is going to be chosen in some sort of fruit in this way dynamically. And as a result, if this contagion wave is going to spread to the whole line, and that means that effectively the only equilibrium in this game must be in this model that everybody is playing zero. Okay, so that's the kind of classic arguments from 20 years ago. Now I want to do the same, but with random utility payoffs. So it's a sort of preliminary step. I will think about also peopling on the line, but kind of to simplify my job, I will assume that each point on the line corresponds to the continuum of agents. And this will allow me to model the heterogeneity not as kind of discrete, but as a continuum problem, because for each node, I will know that there's a continuum of agents, so I can replace them really by a distribution of thresholds, by some sort of law of large numbers. So think about this. There is a place I, and the graph here describes a density of the connections between individual I and the locations to the left, as well as the locations to the right. Okay, G is this density of the connection, and function F is essentially a cumulative distribution of the connections less than J. And I'm going to assume that this my life network is entirely kind of what is the word, is locationally invariant to translation. So it means that the cumulative distribution, the mass of the connections between I and J depends only on the distance between I and J. Okay. That's an assumption. I'm constructing a network here for which I'm trying to show that the contagion will spread, so I can do that. Now, there are some, so this FFJ is exactly defined by this formula, and that's pretty much the only thing that you need to remember on this slide. Again, I'm going to assume that zero is random utility dominant. That is not exactly correct given one of the assumptions of the theorem when I showed that, when I assumed that, there are some agents for whom playing one is strictly dominant, but let's just ignore it for a second for the sake of the developing intuition. So what does it mean that X star is random utility dominant is that the value of this integral is always smaller than zero for every positive X. When X is equal to zero, exactly here, the value of this integral is exactly equal to zero, and then it will be the maximizer of this expression. Okay. So what I want to do is to show that the contagion, similarly, in the deterministic case, will take everybody to playing action zero. Okay, so let's start with the same thought experiment. We have some group of initial infectors. Maybe these are the people who chose playing zero because it was strictly dominant for them. And then there is a boundary and everybody else is playing 1. Now, the person here, or the person, that's not one individual anymore, it's a continuum of agents. All of them have half of their neighbors on this side and another half of the neighbors on this side. There's a continuum of agents, they have all different thresholds, and some of them will want to switch to playing 0, some of them will have sufficiently high thresholds, above half, that they will remain playing 1 as well. Okay, so it's not going to be the case that all of them will switch to playing 0. Only some of them will switch to playing 0. And some fraction of agents to the right of the boundary will also switch to playing 0, but not all of them, okay? And the farther we are away from the boundary, the larger is going to be the necessary, the smaller fraction of their neighbors is playing 0, so the larger is going to be the necessary threshold to induce them to playing 0. So that's why smaller and smaller fraction is going to switch to 0. If this is the case, now that's going to be a new profile. But now if those people switch to playing 0, then we create incentives for new people to switch to playing 0. And those people will start switching. Okay, so it's still going to be a dynamic process. It's not going to be so nice as in the deterministic case where we only had to track the boundary of the contagion wave. Right now, the contagion wave actually will have some shape. Well, suppose, so I want to prove that this contagion wave will take everybody to the bottom, but suppose it does not. Okay, suppose that it stabilizes at certain, in some way. I don't have exactly results to characterize the shape of this contagion wave, but I know at this moment that if it's stable outcome of this best response dynamics, it will have to have some properties. So in particular, some inequalities will have to be satisfied. This is the fraction of agents that is playing 1 in location I. Well, this fraction has to be smaller than so this is the average behavior in their neighborhood that they are observing, this integral inside function P, and this is the fraction of agents for whom the probability that agents have a threshold below this average neighborhood size. So this is the best response number, expected number that should be playing action 1. So because we reach the stable point, it's better be the case than the fraction of agents that is actually playing action 1 is smaller than this best response size. We'll have some inequality here. And this inequality has to be true for every single location. So now some argument is to show that this is true for every single location, then I will have this inequality true as well. And some integration by parts argument. And although that's not exactly stated in the same way, it's easy to show that the second location, the second inequality violates the risk random utility dominant inequalities from few slides back. Okay, so then by contradiction, we show that well, this wave cannot look like this. We have to be exactly at 0. And I will skip the integration by parts argument at this moment because I don't know whether it's not going to helpful. It's simple calculations at this moment. Simple calculation. Okay, so this shows. So far I only looked at line and this toy model where each individual, each location on the line contains a continuum of agents. But that's not my real model. In my real model, I have a network, and each location contains a single individual. And that's a kind of important for me because, one of the stories, where do we get those initial infectors from? If we have sufficiently large network, then we can compute the probability that actually few of the individuals, consecutive group of the individuals will have 0 as a strictly dominant action. So they will always play 0. These are the initial infectors for me. On sufficiently large networks, there is going to be a group of those rebels who will play 0 no matter what. Okay, and I need them to start my contagion argument. Now the problem is that if something like this can happen, I can have this initial infectors. Also, the opposite situation can happen. I can have a consecutive group of individuals for whom 1 is strictly dominant action. Okay, think about them as an obstacle for my contagion wave. If all those people will pay 1 no matter what, then my contagion wave is going to hit this place, but it's not going to convert any of those guys inside, because for them 1 is a strictly dominant action. Okay, this is going to stop the wave. And you know, one thing that you could do at this moment, and this is something that I tried initially, is to compute the relative likelihood of the initial infectors and the obstacles, because maybe there will be some initial infectors of the other side of the obstacle and so on, but that's hopeless. You know, for some distribution of thresholds, the obstacles are much more frequent than the initial infectors. Okay, so nothing like this can work. This is the reason why actually line cannot work as an example for my theorem. I have to go to some other networks, and why I have to go to 2-dimensional networks. So it was very convenient that people have figured out that arguments like contagion, those arguments that I showed you in the deterministic case on the line, they behave very similar in a very similar way when we go to 2 or higher dimensional lattices. And the key step was on the line, as in those higher dimensional lattices, is that on the boundary of the contagion wave, we had to have half of the neighbors to the left and half of the neighbors to the right. Because if we had this, then the risk dominant action becomes best response and the contagion wave can spread. So how does it work on a plane? So on a plane, the neighborhood is some, you know, here I drew a circle, but it's not really important for the argument. Suppose that I have some group of the initial infectors. So for example, individual I, you can see that some of their neighbors I, the individual I is exactly on the boundary of the group of the initial infectors, and some of their neighbors are inside the group of the initial infectors and some are outside, but it's not exactly half. Well, the problem is that the size of this neighborhood is quite large relative to the size of the group of the initial infectors. Let's suppose that the initial infectors, the initial set of infectors is larger. Well, you see that the size, the fraction of the neighbors who are the initial infectors becomes more close to 50%. And actually, if the neighborhood is very, very small relative to curvature of the set of the initial infectors, we are getting closer and closer to 50%. That's the argument from paper by Bloom. Morris is also using it, that actually on lattices, if the size of the initial infectors is sufficiently big, they can initiate the contagion wave that is going to spread in the same way as if it was a line. Okay, because really the only important step is that everywhere along the boundary, we have almost 50% people sitting inside. So the contagion will work exactly the same way. It doesn't matter whether it's deterministic or heterogeneous payoffs. Let's think about the obstacles. The obstacles are not the problem on the 2-dimensional lattice, because the obstacles always look like the compact group of individuals. And on the 2-dimensional lattice, those obstacles are not going to step anything. The contagion wave is just going to go around them. Okay, so this requires some argument, but it's just work. Conceptually, I mean, intuitively, intuition should be clear. Okay, so these were 2 main results, that each network has a fuzzy convention X star equilibrium, some networks have only some such equilibrium. This is possibly, you know, like however you think about it. I want to make a stronger claim that this fuzzy convention X star is actually the natural candidate on every single network. So far, I only know that this fuzzy convention X star is an equilibrium on every network, but I want to show that it's also the most natural equilibrium. Okay, so the argument goes a little bit like this. I'm going to construct a profile. So suppose that you are an individual who does not really know what network you are going to be sitting in. You don't know yet what other people around you are going to be playing. You know your threshold. So I'm going to propose a behavior for you. Well, the behavior for you is compare your threshold to X star. X star is this random utility dominant outcome, you know, maximizer of the integral, and then adopt the behavior if your threshold is below X star, and not play 0 if your threshold is above X star. Okay, you can choose it without knowing anything about your social situation. Now, the results, so this behavior, if people are going to choose this, will result in a fuzzy convention with a large probability, fuzzy convention X star. But is it an equilibrium? So the results that I've proven, when you look a little bit more carefully in what they say and how the proofs work, they actually show that this behavior that I can adopt, not knowing anything about the population, about what equilibrium we are going to play, is actually very close to equilibrium, in the following sense that maybe there will be some individuals who are not playing an equilibrium action, and maybe they will need to revise their action. But this going to be a small fraction of individuals, and if all of them will adapt, revise their action up and down, we will reach an equilibrium that is very close to the original one. Very close in the sense that almost all individuals will stay with the same equilibrium behavior as they chose in the beginning. And this profile is essentially the only profile with this property. Okay, the fuzzy convention X star is essentially the only profile that has this property that we can choose behavior without knowing what everybody else is doing and what is going to be the topology of the network. Okay, so that's it. So that's what I wanted to say, that I talked about the heterogeneous payoffs in coordination games on networks. The network had two key assumptions for my results were that the network has a large degree and the payoff shocks are independent. And both assumptions are important, especially large degree. So this is kind of the biggest complaint that I got, that all my results are asymptotic and they require, going to infinity with the number of neighbors for each individual. I wanted to show you some simulations at the beginning that that's not necessarily the case, that 100 neighbors is not outrageous to think for applications like joining a riot or wearing a mask. I propose kind of a definition what a heterogeneous convention may be, and according to this definition, a behavior is called convention if everybody in the society observes people around them doing, on average, the average behavior around them is the same, or close to it the same. And the result is equilibrium selection theory that generalizes Harsanyi-Zeltem risk dominance to games with heterogeneous payoffs.
Yeah, I would have a question. So you're in your prose version of the statements, you always talk about the networks, but it's really like a sequence of networks, right? And the definition seems to be with like a deterministic limit. Are there like random network models that give you this kind of assumptions, high probability, or because everything has to hold uniform, right?
Sorry, so you talk about this limit, right?
Yeah, I mean, or the assumptions you had before, I think.
So the network is deterministic. So the randomness here comes only from the payoff shocks.
But it's a sequence of networks, right?
It's sequence of networks, like the asymptotic. Yeah. So give me any sequence of networks that satisfy those two properties, then the result will hold. Now, if you want to choose those networks randomly, that's fine with me, because it still will be a sequence of networks that satisfy those properties. But so it's kind of strong in the sense that, it works for every network or every sequence of networks that satisfy those two properties.
But to like standard random network models give you the assumptions high probability, because everything really has to hold very uniform, right? Over all pairs of agents. So this seems to be pretty strong.
So the only uniform assumption is, I see. So both, okay, so very good. So let's look at those assumptions. They are kind of uniform across the... Yeah. That's a good question. So I think, I don't know. So that's a good question. So like, for example, suppose that I take Erdos-Renyi network and take the number of individuals to infinity and the number of neighbors also to infinity a little bit slower. So it does not have to go slower actually so more precisely, the Erdos network has this parameter P, and I take P. The only important thing is that P does not converge to 0. So the question is whether I don't know. I didn't check. I mean, it is possible that actually it satisfies, but like I can easily come up with some random models that actually you are right that this is very uniform. There's kind of for the random graphs, I can see that it can be kind of strong assumption. So I didn't really fiddle too much with those assumptions, and I'm pretty sure that they can be weakened in the sense that they don't need to hold for every single individual, but for almost all individuals. And similarly here.
Yeah.
That's not this results are going to be robust to the existence, of kings and queens, people who are connected to everybody. It's not going to change anything.
Yeah.
The only thing is important is that it's not like 20% of the society are kings and 80% are paupers. That's important.
Yeah. Okay.
But yeah, like, to be honest, it's not that I have a proof. That it's simply the way that I think about those proofs. It's not going to matter. So then I think if I had this stronger version proof, then I think it would that all the random graphs would easily.
I have more kind of an applied question. So it seems kind of very relevant if we think about, the sustainability transition. There are many papers written that people are norm conformist, and there are some policy interventions that we try to do, kind of telling your neighbors are, living sustainably, and then you should live sustainably too. In a sense, I have a paper that shows that people, if they exert a negative externality on someone, that they care how many other people in society do that. So in a sense, it's very important to understand that. And my question, maybe unfair given your model, is, are there any policy implications from your model? So how should we, how can we get to the good equilibrium?
Okay, so I mean, so there is some implementation literature on telling you how, like if you have a coordination game. I mean, it's an old question. It's not just sustainability of, like, the classic example of coordination games are the development models, right? Like when you can have, the railroad and the mine at the same time, but it does not make sense to build mine without railroad. And so there is some literature on implementation in coordination games and how to do that, and like how to push people to equilibrium. And I guess, like the only thing I would say, I mean, not some, like it's important actually. And I believe that there are also like applied papers on this way, like you can pay people for some behavior. No, I mean, I know, like, so I think Sylvain Chassaing has some papers on this, but there is something much older, much older than that. So I know that I've seen, like, this year some job market paper where, or maybe not this year, maybe in the last 2 years, a job market paper where I think Sylvain was one of the co-authors when where they were interested in exactly changing the behavior of moving people from one equilibrium to another. But this is I would say orthogonal issue. It's a very good important issue, but orthogonal. Like so, well, I will tell you is what is the natural behavior, and then if you think that the natural behavior is not what you like, you have to start by looking how to change the naturalness of this behavior, right? So you have to have this information. Does it make sense?
Yeah, absolutely. But
so, you need to play with a P distribution. Like if you can change the distribution of thresholds, for example, by motivating people to do action one. I mean, I can even by you can even if you are targeting the distribution of P, maybe it will be very helpful for you to know what is the easiest and least costly way of making the other behavior dominant convention.
But just a follow-up question. It's okay if you can't answer it, or your model doesn't answer it. But can I suppose I can influence network? I'm Elon Musk. I bought Twitter. Can I do something by influencing the network? Can I learn something from your model about this?
Yeah. So okay. So this is a different literature. So like you are. So there is also like which people in the network I need to change the behavior to change the behavior of the whole people on the network. So I have nothing to say about it. So let me just clarify what I just say. Let me look here. This picture. Okay. So what I can tell you is that if you don't like behavior X star, and you like this, and you don't have any information which people live where on networks, but you can design instruments to change the shape of the green function, you can compute what is the optimal way of changing the shape of the green function. Okay, what is the, say, least costly way of changing the behavior of green function so that the random utility dominant outcome shifts somewhere here? Okay, so if your policy intervention is, well, I know I have information who is where on network and who is influential guy on Twitter, I have nothing to say about it. But if you don't have that information, you only have information, general information about the payoff parameters, then, you know, there are some stuff that you can do.
Yeah, thank you very much. I apologize for the out of scope questions.
No, that's
just what's going
relevant.
through my
Actually,
mind
very good.
your
Like I should do this calculation myself at certain moment, so it's something that I may do. So it's a great question. Thank you.
So is there something like a limit graph game on which you can do these things? Because this reminded me, especially last argument a bit, if you know this, there's this Ehud-Kalai, this expostability of Nash equilibrium. You kind of have like a continuum equilibrium, and for large games, this is with very high probability, basically an epsilon equilibrium, and they use also this kind of concentration arguments. And it seems like there's something like that. Your last argument, you take this very large myopic game and then show that the realizations are with high probability, some kind of, well, approximate equilibrium notion.
I mean, I in the end, I'm looking at real equilibria, right? Not just approximate equilibria, but like arguably it's a little bit easier in my case because I'm looking at coordination games. I think Ehud is working with general games.
But you have a small fraction of people who don't play equilibria, right? You're allowed that it's this.
I see. The very last part of my talk.
Yeah,
right? So it is approximate equilibrium in some sense, right? Like, so whatever is the definition. So some definition of the approximate equilibrium say that everybody differs from the equilibrium action by epsilon. Yeah. And you are right that there are some kind of more generous definition that allows some fraction of the population of playing. Right. So this profile that I defined at the very end, where you simply look at your threshold, compare it to X star, and decide your behavior depending whether your threshold is below X star or above X star, will be approximate equilibrium on every single network.
Okay. Okay. Thank you.
Oh, precisely. The statement is that give me a network. I choose this behavior, then draw a realization of the thresholds. For almost all realization of the threshold, this behavior is going to be an approximate equilibrium on this network, no matter what was the original network. But you know, if you fix the behavior and start changing the network, then of course it will stop being an approximate equilibrium, because you can always find a network that all the zeros are. I mean, you know, you can manipulate with things, right?